Our very first speaker is Elise Gabriel, and I'll introduce her briefly as she gets set up over here. So after a couple of career stops in Europe, Elise is now in the US at Scripps Institution of Oceanography. She's an associate professor there, and we are so blessed and happy to have her on this side of the Atlantic, where she's doing some awesome work. Elise works at the intersection between applied math, computer science, and geophysics. More specifically, she uses high-end computing to model these dynamic, complex earthquake ruptures. And then she looks at the ground motions from that, or the tsunamis being generated from that, and try and match that up with these data sets that we are collecting at present, especially highly detailed ones, like the type of data RuFZO is aiming to collect. And so, Elise, if you are ready.
I'm ready.
The crowd is ready for you.
Thank you. Thank you very much for the introduction. Thanks for the invite. So, good morning, everyone. I will talk about data-driven and physics-based earthquake simulations informed from rupture observations. And the key message of this talk will be that data-driven and physics-based don't have to be mutually exclusive. And I will go through a couple of examples of recent work that's hopefully illustrating the science questions that we could answer with the RuFZO. And I have a couple of examples that will pop out throughout the talk already on the title slide. This is a little teaser. So we have here on the left, broadband, fully physics-based broadband current motion modelings from the Ahmed earthquake in Italy, which is based on 1 million dynamic rupture models that were visited throughout the Bayesian dynamic strong current motion inversion. In the middle panel, you see after slip evolving. So this is a model which is combining co-seismic and three-month geodetic Bayesian inversion for the Parkfield earthquake. That's work in preparation. And we have a multi-scale cascading dynamic rupture simulation, which is modeling volumetric seismicity across a damage zone, which is eventually activating a main fault earthquake. Let's see. Okay, super. All right, so what do I mean with physics-based earthquake modeling? Can mean two things, and I will talk about two kind of aspects of that. The first thing is that we're really interested in getting more physics into the wave propagation part of these models. So that can mean that we are interested in coupling effects of 3D topography with anisotropy, poor elasticity, and lately the conversion of acoustic and seismic waves. And we're also interested in looking at the physics of earthquakes using dynamic rupture models. So that means we solve at the same time for spontaneous frictional failure of rocks under pre-stress, which is nonlinear interacting with the seismic waves that are being generated. And a few examples here. This is one earthquake tsunami model that I will not talk about much today, obviously. But here we've been combining dynamic rupture, seismic, and acoustic wave propagation in the ocean and tsunami generation in one fully coupled multiphysics model. And we also know that from much simpler models, I'll use this. That simple models, analytical analysis reveal already kind of a nonlinear zoo of earthquake rupture styles, including slow and fast ruptures, subshear and supershear rupture, crack and pulses, and slip reactivation. So we see a lot of complexity even in simple models. Now, if we're doing that on scale of real earthquakes, we can strive to fully integrate the observations that we can collect. And that typical workflow of these models is shown here. So we have geological information that can be 3D velocity models, topography, complicated fault structure being put together with rheology, on fault and off fault, for example, constrained on very different scales by friction experiments, initial fault loading. We put that in a computational mesh, we solve, we get synthetics that can be current deformation or synthetic seismograms, and we can tackle really different applications with that. We can highlight what happens in terms of fundamental physics, but we can also bridge scales and make these kind of data fully interacting in this interdisciplinary sense. Now, if we look at recent advances in this kind of modeling, I want to make the point that we can now probe complex fault zone mechanics. So really at the stage where we're beyond modeling slip on a planar predefined single fault plane. We know that faults and fractures host dynamic slip over more than 6 orders of magnitude. So that would be my first example in source dimension. So here's a result from Europe, where we see a machine learning based high resolution earthquake catalog revealing just how complex fault structures are that were activated during the Central Italy sequence. Here's another example where you can also see that these different sizes of fractures and faults that can host dynamic slip are not necessarily acting in an isolated sense, but they're interacting with each other. So this is damage zone heterogeneity mapped in a seismogenic fault in the Borrego Fault in Baja California. And these are all the different fractures that are intersecting in the damage zone mapped out by work of Tom Mitchell's group. Now, if you're trying to model that, we quickly see that we have to extend our understanding of earthquake physics. So in this model that is playing here, you see slip rates, so how much, how dynamic rupture is propagating in a cascading multiscale rupture model that's consisting of here 900 fractures that are all intersecting and that are resembling a fault damage zone, and they're activating at some point something that will resemble a magnitude 6 earthquake here. So to be able to do these models, we have to rethink, for example, how we're imposing friction laws, or how we understand frictional models in these kind of models. So for doing this here, we use a linearly size-dependent fracture energy to be able to do that. So each of these fractures and the main fault have a slightly different scaling in terms of the energy budget that they're experiencing during the earthquake rupturing through the system. And then we can look at the potential observables that these simulations generate. So for example, we see a very diverse slip directions of these upward fractures. We can also see that an equivalent moment tensor that would be seen further from the far field of this kind of complex scenario would have a slight offset with respect to the main fault orientation, which is due to the participation of the fracture network in the dynamic rupture. We can probe the system, for example, by varying pre-stress. So now you see 3 different scenarios of the same system, where we're changing the direction of the relative pre-stress, favoring either the fracture network or the main fault being more optimally pre-stressed. So if we have unfavorable pre-stressed fractures, we can see that we have more of a classical dynamic rupture simulation where we host a large earthquake on the main fault and we have some activation of the off-fault fractures. Whereas when the fracture network is more optimally oriented, we can model fully sustained rupture cascades living completely in the volumetric fracture network, breaking through that as a pulse with a band of fractures actively slipping at any point in time. And this can also generate a sizable earthquake. If you're comparing the moment rate release, especially the spectra of the moment rate, we can see that those 2 examples that do have cascades in the damage zone evolving have a slightly elevated high frequency radiation here. And that brings me to the next slide, where we can think about if any of this would be observable, and potentially observable features include, as I just said, that any of these examples that do include fracture network activation have a slightly elevated high frequency radiation. And there's also other really intriguing aspects of that. So for example, we can define a cascading rupture speed. So that would be the apparent rupture speed as slip propagates through this complicated fracture network, which is shown here. And if we have this, so this is kind of the classical example, rupture speed relatively fast. So if we have the network activated during rupture, we see slower apparent cascading rupture speed. We also have short rise times, so this favors pulse-like ruptures. The moment rate release would have multiple peaks reflecting the complexity. We have slightly elevated average stress drops. So it would be stress drops with hypercentral distance. This is the main fault. These are all the fractures, individual stress drops when they're breaking. For the cases where we have this volumetric multiscale cascades, we see that this is slightly elevated. And we see this diverse slip directions and off-fault fractures. And I compare this here to an inferred fracture map of the ridge-crest earthquakes, where we also see this diversity in rate direction, which cannot be fully explained only by mapping out the Coulomb stress pattern. Now, this has implications for earthquake physics. So for example, we can think about different earthquake initiation mechanisms. So this is an adaptation here from the McClaskey paper in 2019, where we're saying that maybe, this kind of dynamic rupture cascades could be one mechanism how stresses can be redistributed by cascading ruptures in these networks and can assist in nucleation of larger events when they, even if the main fault is very weak. So what we're seeing in the simulation is the main fault is weak, it's not optimally oriented, but the redistribution of dynamic stresses by off-fault seismicity can actually lead to the initiation of a large earthquake. We can also think about this even more fundamentally, and this is now linked to the physics that we put into this model, because we're proposing that there's fundamentally different processes that are driving earthquakes at small and at large slip scales. So what we did here is that we've been correcting seismological inferences of fracture energy with ruptured fault size. If you're plotting the data set, this was published in the SCEC 2015. If you're plotting this as fracture energy over ruptured fault size, you get this kind of gray cloud here, showing a large variability in fracture energy, and kind of a cloud of points. Now we can use an analytical model to correct for the part of the physics that might be invisible in the data that we have currently. There's a lot of discussion about fracture energy and what we may not see in terms of the physics that govern the whole energy budget of earthquakes. But we come up with one model that is correcting that, and it turns out that we can come up with a very simple linear scaling of the minimum fracture energy with ruptured fault size. And that really links to a break in scaling if we plot that against coseismic slip, where we have small earthquakes being governed by dominantly governed by different kind of physics than large earthquakes. So all of this goes into these models that I just showed, because we need some physical, we were interested in coming up with a physical mechanism to explain how earthquakes can nucleate and propagate over 6 orders of magnitude of size. And potential physical explanation could be localization. Coseismic localization may explain onset of flash heating weakening, and then which is governing small slip, whereas then subsequent post-localization slip would favor the more efficient onset of thermal pressurization, which is a mechanism that is more that is better in explaining continuing weakening with slip. So that would be more on this side of this diagram, the large slip fracture energy. Another example, this is now more about the wave propagation parts of how we can look into more data sets or very interdisciplinary data sets, and it can integrate them in these kind of models. So now we're switching sites. This is Finland. Here's Helsinki. Here's an enhanced geothermal system just in the bay in the middle of the city of Helsinki. And there's a lot of observational data throughout the simulation, which doesn't only include seismometers, but also acoustic sensors. And the largest event that was produced during this simulation was a local magnitude 1.8, and there was numerous citizen reports of felt and heard nuisances during the simulation. So there was a lot of citizen reports mapping out earthquake sounds, bangs and crumbling sounds, and really annoying little earthquakes that are disturbing the citizens in Helsinki. And actually, yeah, nobody complained so much about the shaking, but the sounds were really the biggest nuisance, it seems. We've been coming up with a simulation that was published this year, earlier this year in SCEC, where we coupling seismic wave propagation and acoustic wave propagation in the air in a fully coupled sense. And we scaled this up because we're interested in using large computational resources to do these models to 25 Hertz, which is just at the limit of the audible frequency bands. We would really like to do that actually in higher frequencies, but this is kind of what we could do easily. And we find a couple of interesting results. So first of all, the S wave is generating the strongest sound disturbances in the epicentral area. We also see that the shaking and the sound pressure patterns correlate with the earthquake source mechanisms. Stronger than topography does. We do see that topography can lead to some nonlinear effects, but we can really recover in the earthquake sound reports the source mechanisms of these very small earthquakes. So while these kind of sounds can be perceived as disturbing and are a complex sensation, they do carry information even caused by very small earthquakes, and it's really interesting to put these kind of data sets together and trying to, for example, constrain the focal mechanism of small earthquakes. The next example is dynamic earthquake source inversion. I already talked about this a little bit on a title slide. So we've been interested in not inverting for slip patterns, but inverting for the physics of earthquake using near fault data. And we did this first for the Ahmed earthquake, where we had a dense network of 23 components from motion stations within 50 kilometers to the fault. And if you're setting up this inversion, it is a highly nonlinear, very high dimensional forward problem. And we don't have gradients, which is kind of a nightmare for anyone that you talk about in applied math. So we're tackling that with brute force. We're using Bayesian framework, using parallel tempering Monte Carlo Markov chain algorithm. And this is one of the best fitting models for the matrice earthquake. And due to computation constraints, we did this up to a half hertz, 0.5 hertz. It's already interesting. We see dynamic rupture initiating as a weak crack with large rise times, then turns into a pulse with short rise times and other things. But we're really interested in doing this or enhancing this to higher frequencies as well. One of the advantages of using a Bayesian framework is that we get also uncertainty. So this is, for example, the inferred probable mean of slip, stress drop, rise time, and the posterior probability density values. We also get quite a nice match with the observed stations. Not necessarily worse than a kinematic inversion. We also see that most of the complexity of this model is mapped into the frictional weakening length scale, so D sub C. So this again links to fracture energy. So this is the highly heterogeneous parameter with the largest variance. Now, we're getting that into a broadband dynamic into a broadband count motion model, maybe up to 5 hertz. What we can do, we can't do that yet on the scale of running 1 million forward models, but we can take what we know about earthquake physics to enhance the smooth model that is the result of the Bayesian inversion, and we're adding fault roughness, heterogeneities on fault, viscoelastic attenuation, and topography. These are things that we know affect in fully physics-based models the ground motions. And by doing that, we're not only producing, maybe more realistic earthquake models. So here you can see how the fault morphology changes, how the initial shear stress changes if we're adding fault roughness, but how the smooth rupture features remain the same. But we can also, by requiring this consistency at long periods, we can quantify the role of different aspects of earthquake physics. So for example, in this model, by constraining that the large scale rupture dynamics should be the same when we're adding roughness, we can quantify the 3D roughness track, which was in this case an additional resistance to rupture about 3 megapascal using the broadband seismic waveforms. So this is our result. We can see that the high frequency count motions are amplified early on by fault roughness, while topography induced scattering prolongs the duration of shaking. So here we would see the smooth reference model and black out observations. In green, it's just adding fault roughness without topography. So we see elevation in high frequency radiation, but then we really need topography and fault roughness to get also the long duration of the shaking and match the frequency content of the observation. So we can turn on and off different aspects of physics and see what the effect is on our observables. Now, we can bridge timescales of faulting from co-seismic to post-seismic slip. And there has been a paper by Jan Premos, published in Science Advances, doing that for the 214 South Napa earthquake, where we're changing the friction load rate and state friction and invert co-seismic and post-seismic data sets to explain earthquake slip across timescales. That means there are more variables to invert for, but there are also more and complementary observations that we can use. We've been doing that now for Parkfield, and I really wanted to show that today. And just a couple of points here. So we've been using 35 seismic and 13 GPS stations, and this is a preliminary work, so I'm really happy about any comments that recorded similarly large core and post-seismic slip. So now we want to use these stations to constrain at least 868 model parameters on the co-seismic scale and 1,100 in total core and post-seismic. So if you're looking at these numbers, you can already see that it will be very difficult to argue that this is a global minimum in terms of a best model. It's very tricky to do that. Even though we could say we have all these stations, for example, to do a dynamic source inversion, we would really benefit from having more data. It's just a very high dimensional problem. But these are the first results. This is the co-seismic phase and the post-seismic phase. We see for the Parkfield earthquake, one of the best studied earthquakes, I would say, that is available. We do see really interesting aspects. For example, co-seismically, that we have a strongly radiating pulse succeeding by a gentler radiating crack-like rupture. So there's two phases of co-seismic rupture. We also confirm a seamless transition from co-seismic to post-seismic slip. And lastly, if you're looking at this plot, we do see in our case that after slip drives after shocks, not the other way around and not completely co-evolving, but we first see after slip evolving and then after shocks appearing. Okay, so how can a fault zone observatory in synergy with rupture dynamics advance our field? Here's a recent example where we studied in couple dynamic rupture models the link between California's between the ridge-crest earthquakes. We've been including regional structure, ambient long and short-term stresses, and post-seismic fault system interaction to understand the dynamics and delays of the sequence. And here's just one. I don't go into the details because I think this was presented at SCEC before, but we can really use all of these different observables from back projection, static GPS, surface displacements, continuous GPS, ground velocity, so far field recordings, to constrain dynamic models that can explain the complexity of the events. And what we also see in a similar effort by turning on and off different ingredients is that we do need all of these information to understand the dynamics and the delays of the sequence. We've been continuing to work on this model, and we would have already showed one aspect of adding a fault zone. We've been also looking into the extreme near-fault ground motions. We've been adding fault roughness. We've been running that at very high resolution using all of Frontera. And one of the things that we find is that the synthetic ground motions considerably exceed GMPs at distances very close to the fault. So distances closer than 5 kilometers. So here we see PGD, PGV, and PGA of the main shock on the main shock and the foreshock measured at the surface. And these kind of models allow us to probe ground motion parameters, in this case at 2 million surface receivers, so really densely spaced. And we can compare this to GMPs, and we see this stark difference at 5 kilometers to the fault. We can also map this out and plot, for example, elastic shear strain. So this is just something that is a direct model output. We look at the stress tensor, and we see this kind of lightning strikes. And I know that this was something that was also shown in some of the early shakeout scenarios, which is really interesting because it shows rupture complexity. So some of these lightning strikes are linked to surface rupture in the dynamic rupture model, or rupture jumping from segment to segment. So this maps into shear deformation complexity, not only close to the fault, but radiating really in quite large distances to the. And what we show here lastly is the deformation in the volume. So these are binned mean values. This is 81 million receivers. So imagine we could have 81 million stations in the volume and measure elastic and plastic deformation. And what's interesting here is that very close to the fault, so this is 200 meters, the plastic deformation, so the inelastic components are exceeding the elastic strain, but this signal vanishes really quickly at distances larger than 2 kilometers. But the decay rate and the decay rate of the elastic strain changes are changing as soon as the impact of this plastic deformation is not as big anymore. So this is important if you're thinking about what we might measure with, for example, a gas network. So in summary, I showed some examples. I hope I convinced you that data-driven and physics-based earthquake simulations are feasible. We can routinely include observational constraints. We can unify and probe some of these models, for example, that are purely data-driven in terms of dynamic possibility and reduce non-uniqueness. And there's a lot of fundamental earthquake physics that remain to be discovered. So, for example, distributed versus localized fault slip, short versus long-term slip, and evolution of the fault system, and also what are the drivers of complexities and the scaling of small and large earthquakes. So these are really fundamental questions that remain unresolved and where we can come up with hypotheses and probe them against the data. Thank you.
Fascinating stuff. Way above my pay grade. We've got like 5 minutes for questions, and are there any early career people, maybe students, postdocs? We want to give them a chance maybe to ask a question first. Any early career people? Don't be shy. Yeah, go with that.
In this simulation, how do you know the earthquake?
Yeah.
Yeah, it's a good question. So in all of these dynamic rupture simulations, we prescribe nucleation. For Ridgecrest, that's interesting because we were interested to understand better why there was a 34-hour delay between the foreshock that we model and the main shock. And we can quantify the additional shear stress that we need to nucleate the second event, even though it saw all the dynamic and static stress changes the first event, and we can be integrating that to better understand the driving mechanisms. In this case, we can make an argument that this is equivalent to stresses being transferred by afterslip. But these are not seismic cycle simulations that I showed. These are all co-seismic dynamic rupture scale simulations. The dynamic source inversion, where we're including 3 months of afterslip, still doesn't have any other seismicity evolving. It's a dynamic rupture part of the source inversion plus the quasi-dynamic afterslip evolution. So none of this is seismic cycle simulations, but I might show some later in the meeting.
Questions?
So I think, for representing programs using like a factor networks, right? And
yeah.
Then the locations of your place are really used to approximate the factor locations. So how do you think that with that certainty of the locations of your place and affect, like how we represent the factor networks?
Yeah, that's also a good question. So in these models we can choose where we initiate ruptures. We did some experiments where we've been using volumetric overstress. We were interested in induced earthquakes, and we are trying to understand what would happen if you have an overpressure and overstress in the fracture network versus on the main fault. And it seems that like this kind of cascading behavior can happen if you nucleate in the damage zone or on the main fault. So yeah, but dynamics are quite different. So we would really see very different behavioral reaction of the system, depending on where the hypercenter or the first hypercenter would be. So yeah, would be really nice to get a better, as I say here on the slide, would be really nice to better understand which parts of the rupture physics that we observe is localized versus distributed. I think this is really a key question that we have to get more insight on.
Oh, I think at the back we had before we go to
Yeah.
Near-fall exceedance of the ground motion, is that a lack of a physical model, or is it a lack of observations near-fall? Is that one of the great science questions? Because highly relevant for risk forecast.
It is, yes. Yeah, absolutely. And we did the same analysis for a buried normal fault, and we see very different behavior. So it might be linked to surface rupture. Yeah, it would be very interesting to get more data that we can compare that to, right? For Ridgecrest, we have a relatively good data set, but we would be really interested in comparing that to maybe normal faulting events or events that are buried, that are not surface breaking. Yeah, and it's not only relevant for risk, but we really see information on the complexity of the rupture in this data. You can see if you would map out this, if you would have these kind of dense observations of strain, you can see this complexity really mirroring what happens on the faults. It would be great to get that. But I mean, I'm more from the fundamental aspect, but also from the risk aspect. Yeah.
one more, and then we'll move on.
Very nice talk, thank you. One question, right, regarding this workshop is, I mean, you have these amazing set of tools, right, that can simulate quite complex ruptures with roughness, presumably with some dilatation and things like that. Can they be used to ask the question, what would be the optimal design to constrain some of the things that we do not know now, and will the current network design achieve these goals?
That is a good question. There are actually tools in applied math that are looking into optimal experimental design that would be really interesting to use, but I haven't done that. But these models that I showed, where we already have 1 million of forward models, this is a really useful data set for optimal experimental design, also for using machine learning methods or other data science aspects to get more information out of that. So the simulation output can be generated, but we need maybe more manpower to look into all of the things we can do with it. More people should do this.
Let's thank Alex again.